Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about this problem. So let's get started. So the problem is given as we are given a number and we have to print all the prime numbers less than or equal to given number. If number is 10, then we have to print all the prime numbers from 1 to 10. So the prime numbers between 1 to 10 are 2, 3, 5 and 7. If number is 20, the prime numbers are going to be 2, 3, 5, 7, 11, 13, 17 and 19. So now please pause this video and think about a solution to solve this problem. Now let's see the brute force approach to solve this problem. So here I have written a function, and in this function we are running a loop from 2 to less than equal to n. And in each iteration I am checking whether the I is prime or not. If I is prime, then we simply print it on screen. So let's say for n equal to 10, we are running this loop from 2 to 10. When I is 2, we check if 2 is prime or not. If it is prime, then we just print 2 on screen. In next iteration, our I becomes 3. We check if 3 is prime or not, and we simply print 3 on screen. And so on and so forth. So this is how this function prints all the prime numbers from 1 to 10, and we get 2, 3, 5, 7 printed on screen. Now let's talk about the time complexity of this function. So how many times our loop is running? So our loop runs n times, right, from 2 to n. And as we have discussed in previous video, that our is prime function takes square root of n times, right, to find if a number is prime or not. So it means the time complexity of this function is going to be big of n square root of n. Clear? Great. So now if you look at this time complexity, it looks like linear time complexity, or even it is greater than linear. So can we optimize this code? Do we have any option to optimize this code? Because this time complexity is too much. We want to reduce our time complexity to less than linear. So let's see how we do it. So if you want to reduce the time complexity of this function to less than n square root of n, then it is possible using this algorithm. And the name of this algorithm is Sieve of Eratosthenes. It is an ancient algorithm for finding all the prime numbers up to given limit, right? And the real cool thing about this algorithm is the time complexity of this algorithm is big O of n log n. And this time complexity is much smaller than this time complexity, right? So the idea of this algorithm is simple. First, create an array of size n plus 1, then mark all the composites as false, and after doing this step you are left with all the prime numbers, right? So let's see how to implement this algorithm in our code. So here you can see this is a basic implementation of Sieve algorithm. So in this code, what we are doing, we are first creating an array of size n plus 1. Then we are populating all the elements of array to true. It means we are assuming that all the elements are by default prime numbers. Correct? Now, next what we are doing, we are running a loop from 2 to square root of n. Right? Why square root of n? Because we have discussed this concept in previous videos that divisors of numbers appear in pair, right? So for example, if a number is 10, then the divisors of number 10 are 2 and 5, 1 and 10, right? So it means the divisors are always appear in pair, and the first divisor is always going to be smaller than equal to square root of n. It means the square root of 10 is what? 3, and 2 is always less than equal to 3. It happens with all the numbers. So if somehow if we find this divisor, then we can say that this number is not a prime number, because in case of prime numbers, the number has only 2 divisors. And if we are anyhow able to find the first divisor of any number, then we can clearly say that this number is not a prime number. So that's why we are running loop from 2 to square root of n. And in this loop, what we are doing, we are simply checking if a given element is prime or not. As we have assumed that all the numbers are by default prime, so that's why we are again checking if a number is prime or not. If the number is prime, then inside of if statement, what we are doing, we are running a loop from I into 2 less than equal to n, and we are marking all the multiple of I to false, right? So this for loop I will explain you in a bit. So at the last, what we are doing, we are again running a loop from 2 to less than equal to n, and we are checking if k is prime. So when we reach to this for loop, we have marked all the composites to false. So that's why we are checking that if a number is prime, it means that number is actually a prime number, and we simply print it on the screen. So let's quickly dry run this code and see how it works. So let's say the n is 10, so the square root of n is going to be 3. So we initialize our array with 10 elements. So we just ignore the 0th and 1 element because 0 and 1 is not considered as prime or composite. So we only care about number from 2 to 10. Okay. So when I is 2, we are going to check if 2 is prime or not. And this condition becomes true because 2 is already marked as true by default. So we enter into this if statement, and then we run a loop from I into 2. It means 2 into 2 is going to be 4. So we run a loop from 4 to less than equal to n, and in each iteration we are increment j by I. Means the first element is going to be 4, then 4 plus I means 4 plus 2 is 6, 6 plus 2 is 8, 8 plus 2 is 10. And we mark all of these elements as false because 2 is our smallest prime number, right? And the multiples of 2 are definitely a composite number. So we are marking 4, 6, 8, 10 to false. It means all these numbers are composite and we do not care about those numbers, correct? So in next iteration I becomes 3, and again we are checking if 3 is prime or not. And this time this condition becomes true, that 3 is prime. And why it is happening? How this code is detecting that 3 is prime? Because if 3 is not prime, then it would have been marked false when we are traversing for 2, correct? So it means it is not marked as false, it means this number is a prime number, correct? And we start with the 3, and we start with 6 because 3 into 2 is equal to 6, and then we move to 3, then we move to 6 plus 3 is equal to 9, and we stop. Okay, and we mark 6 and 9 to false because 6 and 9 are not prime numbers. Why? Because there is a smaller factor of 6 and 9, and that is 3. It means 6 and 9 are factors of 3, so therefore we are marking it false. So far we have marked 4, 6, 8, 9 and 10 as composite numbers. So in next iteration when I becomes 4, our condition becomes false because 4 is not less than equal to 3. So we get out of this loop, and at the last this loop is going to run. So we are simply iterate over all the elements, and we simply print all the elements that has the value true, and ignoring the 0 and 1. We are simply ignoring 1 and 0 because we are not interested in 1 and 0, right? So this is how the sieve of algorithm works. The thing to understand here is that we only reach if condition if the number is prime, right? Let's understand this with an example. So if we take n as equal to 16, so the square root of 16 is going to be 4. So when we run this code, our loop starts with I equal to 2, and we mark all the elements that are multiple of 2, let's say 4, 6, 8, 10, 12, 14, 16 as false because these numbers are composite number. And in next iteration when I becomes 3, we mark all the multiples of 3 that are 6, 9, 12 and 15 because these are also a composite number. Now when I becomes 4, we are not going to enter this if statement. Why? Because if we check that 4 is prime or not, it gives false. Why it gives false? Because 4 has smaller factors, because 4 has been already marked as false when we are traversing for 2, right? See here. So that's why we are not going to enter into 4. So basically we are going to enter into this if statement only if the number is prime, because if the number is not prime, then obviously the smallest factor has already marked it as false. So far so clear. Okay, let's move on. So let's do some optimization over this code. So right now what is happening, we are running a loop from I into 2 till less than equal to n. So here there is a chance that we can optimize this code better. So if we look at this example, when I is 2, we are marking 4, 6, 8 and 10 to false, and when I is 3, again we are marking 6 to false. So we are doing redundant work here. So here is a chance to optimize this code. So let's see how we can optimize this code. So let's say if n is 25, then when I is 2, we are checking for I square. It means we are starting from 4. Then we check for 4 plus 2, 6. Then we check for 6 plus 2, 8, and then 10, right? So when we reach I equal to 5, we would be checking for I equal to 10, 15, 20 and 25. But we are unnecessarily checking 10, 15 and 20. Why? Because 10 is a factor of 2, 15 is a factor of 3 and 20 is also a factor of 2. So it means when we were running our loop for 2 and 3, it would have been marked as false, right? So we are unnecessarily checking this. So we can avoid checking all these numbers. So to avoid checking all these numbers, instead of running a loop from I into 2, we can simply start our loop from I cross I. So in case of 5, now we do not need to check for 10, 15, 20. We simply start our loop from 25, right? So this is the optimization we can do here. So I have simply replaced the code from I into 2 to I into I. Okay, so this is the optimization we have done in this code. After optimization also there is a room to reduce the number of code. So let's see how we can reduce the number of code of this program. Okay, so this is the shorter implementation of Sieve algorithm. And what we are doing here, we are simply creating an array of size n plus 1 and populating it with true, right? And next, instead of running a loop from 2 to square root of n, we are running a loop from 2 to less than equal to n. Why we are doing this, I will explain you in a bit. And then we are checking that if I is prime or not. And if I is prime, then we simply print it on the screen. And we know the reason why we are printing this on a screen. We have discussed before that the condition of if statement becomes true only if the number is prime. That's why we are sure and we are simply printing it on screen. So that's why we are sure that whenever we reach here, the number must be prime. So that's why we are simply printing it on screen, right? Now after printing it on screen, we simply running a loop from I into I till less than equal to n, and we are marking all the elements as false. So let's see the working of this code with an example. So let's say if n is 10, the square root of 10 is 3, right? So in first iteration our I is 2, correct? So first of all it gets printed on the screen. Then we mark all the multiples of 2 as false, and that is 4, 6, 8 and 10. Now in next iteration our I becomes 3, and we are sure that 3 is a prime number. We have discussed the reason why it is that. So we simply print 3 on the screen, right? And we mark all the multiple of 3 to false. 3 into 3 is 9. So we start from 9. And 9 is the last number. And in next iteration when I becomes 4, the if statement checks if 4 is prime or not. So we would have already marked 4 as false, so this condition becomes false and we are never going to enter into if statement, right? In next iteration our I becomes 5 and it checks if 5 is prime or not. 5 is prime, so the 5 gets printed on the screen. We run a loop from 5 into 5, 25 till n and mark all the composite numbers or multiple of 5 to false, right? So in next iteration I becomes 6, nothing happens, and after I become 7, and 7 is also a prime number, so 7 gets printed on the screen. So this is how Sieve algorithm prints all the prime numbers from 1 to a given number. and this is our shortest implementation of sieve algorithm. So I hope you understood this sieve algorithm clearly, and now you have a good understanding of sieve algorithm and how it works. So this is it for this video. Thanks for watching. See you in the next video.